Hey folks, so I'm just making a short video for you on the concept of power. And to get us started, this is the problem I want you to consider. You have two people, all right, person A and person B. And just to make things easy, let's say the mass of each person is 100 kilograms. So identical mass people. And they're each going to run at 2 meters per second at a constant speed of 2 meters per second up this ramp. And eventually they'll meet at the top, still running into each other at 2 meters per second. So the question we want to consider is how much work does each person need to do to get to the top? And you could think about work as force times distance. You can work out the answer to this problem in that way, but a much nicer way to think about this is the work done by either person here uh, results in the following energy transduction. Chemical energy in the person's body goes down, and gravitational potential energy is what replaces it. So really, how much work a person does here is just how much gravitational potential energy each person gains at the expense of chemical energy, which is lost. Kinetic energy is not involved in this at all because the people run at a constant speed up the ramp, which means neither person's kinetic energy is changing. Uh, all that's happening, I'm stressing this several times, is that chemical energy turns into gravitational potential energy. So the work that, let's say, person A does is equal to the change in gravitational potential energy of person A, which is equal to mg delta y. A change in height is leading to a change in gravitational potential energy. Well, let's do that calculation. Person A has a mass of 100 kilograms. The Earth's gravitational field is approximately 10 newtons per kilogram. And I can see from the picture the height that that person A rises, is 6 meters. And this gives us 6,000 joules of work. So person A does 6,000 joules of work. Their chemical energy drops by 6,000 joules. Their gravitational potential energy rises by 6,000 joules. One thing you should notice here is that the same exact calculation applies to person B. Person B has the same mass as person A and also rises 6 meters into the air. So the same amount of work is done by both people in this case, specifically 6,000 joules. So if someone were to ask you, does it require more chemical energy? Do you have to do more work if you run up the steep slope or the more gradual slope? The answer is same amount of work either way. But something does differ between these two people, which is the rate at which they do work. Think about it. Person A has to run 4 meters to get to the top. They're going the more direct, steeper route. So they're moving at 2 meters per second, and they have 4 meters to travel, which means this process here, delta TA, is going to take 2 seconds. On the other hand, person B is kind of taking their time. They're going up the more gradual side of the mountain here. They have to move 8 meters, and they're moving at a rate of 2 meters per second. So delta T for person B is 4 seconds. Although they did the same amount of work, person A had to do that work in a much smaller amount of time. And this is what the idea of power is all about. Okay, power, capital P, is the rate at which work is done. You could also think about it at the rate at which energy is transduced from one form to another. So, as a formula, power is how much work is done divided by the time it takes to do that work, which is the same as the amount of energy that changes from one form to another divided by the time it took that energy transduction process to unfold. So now we can calculate the power output of each person. Work over change in time. Person A does an amount of work equal to 6,000 joules in an amount of time, 2 seconds. And therefore, person A does 3,000 joules of work per second. That is person A's power output, 3,000 joules per second. We have a special name for a joule per second. We use capital W for this unit, and we call it a watt, W-A-T-T. So person A's power output is 3,000 watts. You have to be careful here. We use capital W to stand for work, and we use capital W for the unit of power, which is watts. So keep your eye out for that. There's no easy way to get around actually paying attention to what where the symbols are placed on the paper. All right, person A does 3,000 joules of work per second. Person B also does 6,000 joules of work, but they complete this task in a much more casual 4 seconds, which is 1,500 joules per second or 1,500 watts. The rate at which person A does work is 3,000 joules per second. The rate at which person B does work is 1,500 joules per second. And so their power outputs are different. Now, why is this relevant? Well, first of all, there's a lot of common items where the power of the item is listed on the item. A light bulb does not tell you how many joules of light energy it will give off. That all depends on the time that you're using the bulb over the bulb's lifetime. Let me get the lights one moment. There we go. But what a light bulb does tell you is the rate at which light comes out of the bulb. A 100-watt light bulb releases 100 joules of energy per second. A 200-watt light bulb is even brighter. It releases 200 joules of energy per second. It's like this with car engines, although usually horsepower is it's an equivalent unit of power instead of watts. But it's the power output. It's the rate at which this device will do work, or the rate at which this device will convert one form of energy to another. Okay, so let's talk about something else. How do I scroll down? This is the old Zoom whiteboard. I can't scroll. Okay, so here's another way to think about power. Suppose I have an object, and that object is being pulled with some force. Maybe the force is angled like this. And this object is cruising along at some speed. Okay, here's a question. What is the power delivered by force F? The power delivered by force F to the object is the rate at which the force does work on the object. It's the rate at which the force is attempting to increase the kinetic energy of the object. Well, we said power is work divided by the time it took to do that work. But I know work is F parallel times delta X, force times distance. This force, F, does work because it has a component, F parallel, which is parallel to the displacement. But now I look at this expression and I say, oh, delta X over delta T, that's just the speed. Displacement over time is speed. So the power that force delivers to the object is the part of the force parallel to the displacement times the speed. And this is an equation that pops up now and then. Let's say I want to do work very rapidly on an object. So I want to do many joules of work per second. I want to deliver a power of many watts. That requires applying a large force parallel to the object. And if the object is moving fast already, that results in me doing work at a great rate. The way to appreciate that is just to realize that if the object's moving fast and I'm pushing on it, then it's undergoing a big displacement in a short amount of time, and I'm pushing on it. So I must be doing work on the object very rapidly. Okay, one more item. Power equals work over time. I can write this as the work done by a force equals the power delivered by the force over the time it took, over some time interval. Um, is that what I want? No, it's not what I want. It's not even a correct equation. Multiplying both sides by delta t, I get power times delta t. All right, that equation leads to that equation. I knew something looked funny. All right, so work equals power times time. Uh, let's say you were calibrating some engine in the automotive industry. You might fire the engine up and run it and create a plot of power versus time. Maybe that plot would look something like this. So as the engine gets revving, the power increases. It's doing more and more work per unit time, more joules of work per second. But then it levels off when it's running at maximum, revs. It's approaching a fixed maximum amount of work per unit time, a fixed power. Remember when I multiply two things together, finding the area under a graph of those two things is equivalent to doing that multiplication. All right. So to find the total work done by whatever it is has this power associated with it, what I can do is between two times T1 and T2, I can take the area under this graph. The area under this graph is equivalent to multiplying power times change in time, which is work done. And sometimes information is presented in this way. You'll have a graph of power output versus time for some force or some engine or some device or some person lifting things. And you have to appreciate that for a power versus time graph, the area under it is like multiplying power times change in time. So it's giving you the total amount of work done in that time interval. All right, folks, this should be enough for you to at least make an honest attempt at the power homework. And of course, we'll go over it next class. Thank you so much, and I'll see you in class soon. Bye now.